So, you want to generate an image using Julia, but you don't want to use a plotting package. Even though there are some great plotting packages out there, they often take a long time to load and to compile. Is there a way to generate an image using Julia without using a plotting package? Well, let's find out. Welcome to Doka.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. In today's tutorial, we'll get an introduction to image processing in Julia by using the images.jl package along with Pluto notebooks. We'll also learn what the Mandelbrot set is, and learn how to generate an image of the Mandelbrot set using both the CPU and the GPU without using a plotting package. If you're new to Pluto notebooks, I have 3 videos on how to use Pluto notebooks on this channel. For the GPU portion of this tutorial, you will need access to a computer with a CUDA-compatible GPU manufactured by NVIDIA. If you're new to the CUDA.jl package, I also have 3 videos on how to use the CUDA.jl package on this channel. I have provided links to the Pluto videos, as well as the CUDA.jl videos, in the description below. With that said, let's get started. Images.jl is a fun package that will allow us to convert a Julia matrix into an image without using a plotting package. To see this, let's fire up Pluto and create a new notebook. Let's start by adding the images.jl package as well as the Pluto UI package. The images.jl package supports many different color scales. 2 common color scales are known as grayscale and RGB. Grayscale converts a value from 0 to 1 into a shade of gray. We can see the different shades of gray by using a slider. Zero is black, and 1 is white. In order to display the color, simply call gray. According to the images.jl documentation, N0F8 is a special data type that interprets an 8-bit integer as if it had been scaled by 1 over 255, thus encoding values from 0 to 1 in 256 steps. So, in the slider, there are 1001 values from 0 to 1, but there are only 256 values that can be used on a color scale. So the N0F8 data type does that conversion for you. As you can see, 0 is black and 1 is white. Every value in between is some shade of gray. Fun, right? For color, you need multiple channels. A common color scale is RGB, which stands for red, green, and blue. A combination of these 3 colors will generate any visible color. Again, we can use sliders to see this. In order to display it, all you need to do is call RGB. When all of the values are 0, then the image is black. When the red value is 1, then the image is red. When the green value is 1, then the image is green. When the blue value is 1, then the image is blue. When all of the values are 1, then the image is white. You can combine the values to generate any visible color. Cool, right? You can convert a Julia matrix into an image by extending these concepts. By convention, the size of an image is measured by its width first, and then its height. For a matrix, the width is the number of columns, and the height is the number of rows. It's a little confusing because a Julia matrix is measured by the number of rows first, and then the number of columns. Let's generate some random numbers for our matrix, so each element of the matrix will be a different color. For the data type, we can use gray or RGB. Now, when you change the size of the matrix, the size of the image changes. So that's the basics of using the images.jl package to generate an image from a matrix. If you found that fun and interesting, you can show your appreciation to the developers and contributors of the images.jl package by going to their GitHub page and leaving them a star. Now, we can apply this knowledge to generate an image of the Mandelbrot set. But before we do that, let's learn what the Mandelbrot set is. You've probably seen an image of the Mandelbrot set, like this one. But what is it? This image is drawn onto a two-dimensional plane where the x-axis is the set of real numbers, and the y-axis is the set of imaginary numbers. An imaginary unit is defined as the square root of -1, and is denoted by the lowercase letter I. Otherwise, an imaginary number behaves just like a real number, so you can have 1i, 2i, 3i, and so on. You can also have -1i, -2i, -3i, and so on. A two-dimensional plane with real numbers along the x-axis and imaginary numbers along the y-axis is known as a complex plane. And a point located on this plane is known as a complex number. A complex number is denoted by a real number plus an imaginary number, like 1 plus 2i. The image of the Mandelbrot set is drawn on a complex plane. On this image, the origin is located somewhere around here. The values along the horizontal or real axis range from roughly -2 to roughly +0.5. The values along the vertical or imaginary axis range from roughly -1i to +1i. All of the values colored in black are included in the Mandelbrot set. All the other values in different colors are not included in the Mandelbrot set. So which numbers qualify and which numbers don't? In order to test whether or not a complex number C can be included in the Mandelbrot set, you need to iterate it through the function z equals z squared plus c, where z is also a complex number. The iteration starts with z as in Zulu set equal to c as in Charlie. After passing z through the function, you'll get a new value for z. Then you repeat the process with the new value of z. Again, the result becomes the new value for z. You repeat this process until you can determine what's happening to the value of z. If the value of z tends to infinity, then the complex number is not part of the Mandelbrot set. But if the value of z settles locally, then the complex number is included in the Mandelbrot set. Repeating this process for a range of complex numbers will result in a set of numbers that can be converted into an image that is surprisingly sophisticated and mesmerizing. One of the fascinating properties of this image is that there is no limit to how much you can zoom in on any section along the edge of the Mandelbrot set. It's like looking at something through a microscope and then increasing the magnification only to discover a whole new microscopic world. I'm not aware of any practical application of the Mandelbrot sets, but it has, nevertheless, captured the imagination of both mathematicians and non-mathematicians alike. For this tutorial, we're going to generate a static, grayscale image of the Mandelbrot set using the CPU. And then, we're going to generate an interactive color image of the Mandelbrot set using the GPU that we can use to zoom in on the image so we can explore this strange and beautiful world. Let's start by creating a new Pluto notebook. I took the code for this section from Jeff Bezanson. He gave a webinar on multithreading in Julia, where he demonstrated how to use multithreading to generate an image of the Mandelbrot set. You can watch his video on the Julia Hub YouTube channel, not to be confused with Julia's official YouTube channel. I provided a link to his video in the description below. Next, let's load a couple of packages. In order to generate an image of the Mandelbrot set, we need to create a matrix that will serve as an abstraction of the complex plane. We will need to go through each element of this matrix and iterate over that complex number in order to determine whether or not that complex number belongs in the Mandelbrot set. To do this, we need two functions. One function will define the iteration process that will determine whether or not a complex number belongs in the Mandelbrot set. The other function will loop over the matrix and apply the iterator function to each element of the matrix. The result will be a matrix that we can convert into an image of the Mandelbrot sets. Let's start with the iterator function. I modified this code slightly, but my biggest alteration was to add a lot of comments so I could better understand what the code was doing. C is the complex number to be tested, also known as the point of interest. The iteration process starts by setting Z, as in Zulu, equal to C, as in Charlie. The for loop is the iterator that replaces the value of z with z squared plus c. If the absolute value of z is greater than 2, then it will escape the loop and return the value of the last iterator minus 1. Otherwise, if it survives the maximum number of iterations, then it will return the maximum number of iterations. You can change the value of the maximum number of iterations if you like. Also, the value of z is known to fall between -2 and 2, which is why the absolute value of 2 is used as a test. Next, we need a function that will create a matrix and then loop over each element and apply the iterate function. You can change the default values in the parameters. These default values will generate a matrix that can be converted into an image suitable for a 4K monitor. You can also change the values for the range of the real numbers and imaginary numbers. I'm using a range between -2 and +2 in order to generate a square image. Now we can call our function to generate a matrix. This matrix contains the number of iterations for each element. You can't really see anything in this display because it's just showing the values in the four corners of the matrix, which just happen to be zeros. Each element of this matrix contains an integer between 0 and 400. A value of 400, which is the maximum number of iterations, means that the element is part of the Mandelbrot set. By convention, members of the Mandelbrot set are displayed in black, so we need to find all of the 400s and convert them into zeros. We can do that by broadcasting the modulus operator onto each element to get the remainder when we divide the value by 400. This will preserve all of the other values, but it will convert the 400s into zeros. This slider will allow us to change the contrast of the image, which will provide further insights. So, what are we looking at? The values shown in black are members of the Mandelbrot set. It's a little difficult to see in this image, but the different shades of gray indicate how many iterations it took for the values to escape the test. Darker shades exited very quickly, while lighter shades took longer. That white halo surrounding the Mandelbrot set indicates that those values took a lot of iterations before escaping. You can see this more clearly by using the contrast slider. This black and white image shows the Mandelbrot set in black. That white circle has a radius of 2. Any values outside of the circle is not included in the Mandelbrot set, even though the color is black on this image. Adjusting the contrast to 10 provides a clearer view of how many iterations it took to determine that the value did not belong in the Mandelbrot set. The value shown in white took the longest time to evaluate. Pretty cool, right? You can save this image to disk by using the save function. After saving, you might want to comment this line out or disable the cell. Otherwise, Pluto will continue to save this image to disk every time you make a change to this notebook. Even though this image was created for a 4K monitor, it's still a raster image. This means that when you zoom in, at some point you'll start to see the individual square pixels. Each pixel is an element in our matrix. But one of the fascinating characteristics of the Mandelbrot set is that you should be able to zoom in infinitely. Unfortunately, you can't do that with this image. But we'll learn how to do that in the next section. For this section, I had two objectives. One, I wanted to figure out how to generate an image of the Mandelbrot set using the GPU. And two, I wanted to figure out how to zoom in on the image without losing any detail. These challenges turned out to be much more difficult than I had imagined. Fortunately, someone's already figured out how to do this. I apologize in advance for my pronunciation, but I took the code for this section from the GitHub repository of Vinicius Freires de Almeida. I'll be honest, I don't fully understand how this code works, so all I did was lift this code, and then I added some Pluto sliders so we can move around the image and zoom in on it. Consider this section more of an inspirational demonstration as opposed to a step-by-step coding tutorial. With that said, let's create a new Pluto notebook. For this to work, you will need access to a CUDA-compatible GPU made by NVIDIA. I haven't used the symbolics.jl package before, so I don't know much about it. According to its documentation, symbolics.jl is a fast and modern computer algebra system. Since I can't really explain this code, for the most part, I will simply be copying and pasting code into this Pluto notebook. You can find all of this code in my GitHub repository. I do understand the image dimensions. I'm using the dimensions for a 4K monitor, but feel free to select your own dimensions. I added a couple sliders here. These sliders will allow us to move around the image. I added a slider here as well, so we can zoom in on the image. I can't explain the next several lines of code, so I'm just copying and pasting code here. Okay, I understand this line for the maximum number of iterations. So that's a lot of code before we get to the actual Mandelbrot function. Here's the code for the Mandelbrot function on the GPU. In order to run this function on the GPU, we need to pre-allocate the matrix onto the GPU by using the cuArray constructor. Any calculations performed on the cuArray will be handled by the GPU. Once that's done, we can call the Mandelbrot function to evaluate all of the elements in this matrix. And that's it. This matrix identifies the values that are in the Mandelbrot set. Before generating the image, let's create a refresh button, and then move the sliders down. Now, we can generate the image. Pretty wild, right? Every time you move the sliders, the values in the matrix will recalculate automatically in the GPU. But this image will not refresh automatically. You need to hit that refresh button to see an updated image. Pretty cool, right? Even though the colors are wild, this image shows the same information as our static grayscale image. The solid reddish-pink color indicates the values that are included in the Mandelbrot set. The different colors indicate how many iterations it took to determine that the values did not belong to the Mandelbrot set. In theory, we should be able to zoom in on this image forever. Just for fun, let's pick a spot and keep zooming in to see what happens. How cool is that? There are all sorts of microscopic worlds hidden in this image, just waiting for you to explore. If you enjoyed this demonstration, you can show your appreciation to the author of the source code by going to his GitHub page and by leaving him a star. Like before, you can save your image to disk by using the save function. Again, you might want to comment this line out after saving to disk, or disable the cell. Otherwise, Pluto will automatically save this image to disk every time you refresh the image. Working on this project was a humbling experience for me, but I'm not ashamed to admit that I don't understand everything, and that I still have a lot to learn. But studying the brilliant work of others inspires me to push past my comfort zone, and it motivates me to keep moving forward. Exploring the different regions of the Mandelbrot set was also a nice reminder that not everything is about practical applications. Sometimes, it's nice to just appreciate the universe for what it is. Something strange, and something mysterious, and something terrifying, and something beautiful. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.